So in last class we discussed about switching schemes, right? In last class we discussed about different types of switching scheme and its application where we are using all those switching scheme.
Yes.
Now in today's session we will going to discuss about single line diagrams, and also we are going to understand how we are preparing the single line diagram for any electrical system. Okay, now I think you know what's the single line diagram. First we understand why this diagram is called single line diagram. If you see our electrical system, so our electrical system has a multi-wire. Basically, our electrical system is a multi-wire system. So many wires for a one feeder. And if you see in one feeder, there is a multi-phase also, right? So our electrical system is a multi-wire or multi-phase system. If we want to represent our electrical network in multi-wire and multi-phase system, so what happened? Our diagram, or you can say, look like a complex, right now. So therefore what we are doing, we are representing the multi-wire and multi-phase system in single line. Okay, so therefore this diagram is called single line diagram. Now here question is coming ki what actually represents single line diagram. Single line diagram represent overview of your electrical system. Once you see single line diagram of any electrical system, so you have a clear picture of your electrical network, or you can say of your electrical system. Means at what voltage level your system is working, how much power is flowing in your system, how many numbers of feeders, okay, what are the major components you are using in your system. So all your details you are going to get from a single line diagram. So single line diagram represent overview of your electrical system. Okay, so single line diagram represent your technical parameters. Technical parameter means voltage, frequency, fault current, power, rating. So they represent technical parameters. Single line diagram represent components details. What are the major components you are using in your system? Means watt rating of a breaker, watt rating of a CT, watt rating of a PT, watt rating of a transformer, watt rating of a motor, watt rating of a generator you are using in your system. So single line diagram represent overview of your electrical system. Understand, Hamid and Ganesh, what is actually single line diagram? Single line diagram gives a clear picture of your electrical system. Once you see single line diagram, you have a clear idea how your system is going to be performed. Okay, now here next question is coming, how actually we are preparing the single line diagram, how we can prepare the single line diagram. So single line diagram, wherever we are preparing the single line diagram, for a preparation of single line diagram we require some inputs. Okay, and based on that inputs basically we are preparing the single line diagram. So what inputs you require for a single line diagram? So first input you require, that is just note down inputs required for a single line diagram. First you note down inputs required for a single line diagram. First input, type of system, or you can say type of substation. First input you require type of substation. Type of substation means your substation is generating substation, grid substation, industrial, rural distribution, what type of system. So first input you require type of system, or you can say type of substation. Second input you require type of switching scheme. So what type of switching scheme you are using for your system, this is the second input. Type of switching scheme means I think in last class we have gone through 6 numbers of switching scheme. So what type of switching scheme you are using for a system, so this is decided by you. Basically this input you require for the preparation of single line diagram. After type of switching scheme. Next input you require numbers of incoming feeders and numbers of outgoing feeder. Means in a system how many numbers of incoming feeder you are using and how many numbers of outgoing feeder you are using. This input you require numbers of incoming feeders and numbers of outgoing feeders. Then next input you require voltage level of incoming feeder and voltage level of outgoing feeder. Means what is the voltage level of your incoming feeder and what is the voltage level of your outgoing feeder. The next input you require fault current, or you can say short circuit current rating of your incoming feeder and your outgoing feeder. Short circuit current rating of incoming feeder and your outgoing feeder. Okay. The next input you require after short circuit current rating, the next input you require numbers of transformer and its rating. So these inputs you require for a preparation of single line diagram. So what inputs you require? First, type of system, or you can say type of substation. Second, type of switching scheme. Third, numbers of incoming feeders or numbers of outgoing feeder. And then fourth you require after numbers of feeders, and then fourth you require fault level of incoming feeder and outgoing level feeders. The next input you require numbers of transformer and its rating. So these inputs you require, and based on these inputs you are preparing the single line diagram for any electrical system. Now first input, just note down. For example, with help of a small example questionnaire one, you can say small example, we are going to understand how actually we are preparing the single line diagram. So for example, there is a system, you can say there is substation. That substation is a rural distribution substation. Okay, so first input you require type of system or substation, that is the rural distribution substation. Then next second input you require switching scheme. So what type of switching scheme you are using for a rural distribution substation, Hamid and Ganesh? What type of switching scheme you are using for
Single bus arrangement?
Right, single bus arrangement. So just note down, second input is single bus bar arrangement. The next input you require numbers of incoming feeders and numbers of outgoing feeder. So numbers of incoming feeder, just note down 2, and numbers of outgoing feeder, just note down 2. So you have a 2 numbers of incoming feeders and 2 numbers of outgoing feeder. Then next input you require voltage level of incoming feeder and voltage level of outgoing feeder. So just note down, voltage level of incoming feeder is 33 kV and voltage level of your outgoing feeder is 11 kV. Understand what I am telling, Ahmad and Ganesh?
Okay,
Yes,
sir.
yes, sir.
So voltage level of your incoming feeder is 33 and voltage level outgoing feeder is 11. Now next input you require fault level, or you can say short circuit current level of incoming feeder and outgoing feeder. So short circuit current rating of your incoming and outgoing feeder, how you are deciding? So actually any feeder fault current rating depend on two parameters, your feeder power rating and feeder impedance value. Okay. So actual feeder fault current calculation we are going to learn in coming classes. Okay, how we are calculating the actual fault current rating of any feeder. So that things we are going to learn in coming classes. But we have a standard fault current rating based on voltage level. So just note down a standard fault current rating based on voltage level. Just note down a standard fault current rating based on voltage level. First column is serial number. First column is serial number. Second column is voltage level. Second column is voltage level. Third one is fault current rating in kiloampere. Fault current rating in kiloampere. And the next column is fault current duration time in second. Okay. So first is serial number. Second one is voltage level. Third one is fault current in kiloampere. And fourth one is the duration time in second. Now first your voltage level, serial number 1, voltage level 11 kV, fault current rating 25 kiloampere, 25 kA, duration time 1 second. Then again serial number 2, fault current rating, serial number 2 voltage rating 11 kV, fault current rating 31.5 K, duration time 1 second. Then serial number 3, voltage rating 33 kV, fault current rating 25 K, duration time 1 second. Then again 33 kV system, fault current 31.5 K, duration time 1 second. The next one is 66 kV system, 66 kV, fault current 31.5 K, duration time 1 second. Then next you have a 132 kV system, fault current 31.5 K, duration time 1 second. Again 132 kV system, fault current 40 K, duration time 1 second. Again 220 kV system, fault current 50 K, duration time 1 second. Then you have a 400 kV system, fault current 50 K, duration time 1 second. Then again you have a 400 kV system, fault current 63 K, duration time 1 second. And then in last you have a 765 kV system and fault current 50 K for 1 second. So this is the standard fault current rating based on voltage level. So now your incoming feeder voltage rating is 33 kV. Your outgoing feeder voltage rating is 11 kV. Okay. So what fault current you are going to consider for a incoming feeder and what fault current you are going to consider for a outgoing feeder? So your incoming feeder is 33, outgoing 11. So incoming feeder fault current you are going to consider 25 K. And also for outgoing feeder you are going to consider 25 K. Understand Hamid and Ganesh how you are selecting?
Once again explain, sir. Sorry.
What's the standard fault current rating of your 33 kV feeder? Have you note down fault current rating? Ganesh?
Sir.
Sorry?
Hello?
Yeah,
Sir.
have you note down the standard fault current rating?
No, sir. Some speed.
Why not you are telling here?
Actually 50%.
So basically your 33 kV feeder, a standard fault current rating is 25 kiloampere.
5 K amperes. Yes.
And your 11 kV system, a standard fault current rating is 25 kiloampere. So you are considering fault current rating of your incoming feeder, that is 33 kV. So their fault current rating you are considering 25 kiloampere. And your outgoing feeder is working at voltage level 11 kV and their fault current rating is also 25 kiloampere. Understand now?
Yes, sir.
Now after fault current rating, next what input you require? Numbers of transformer. So just note down numbers of transformer is 2 and its rating is 10 MVA. Numbers of transformer is 2 and its rating is 10 MVA. So these are the inputs.
10
MVA. So
okay,
these
sir.
are the inputs, and based on these inputs we are preparing the single line diagram. How we are preparing the single line diagram based on all these inputs? So basically your single line diagram represent system parameters like voltage, frequency, fault current, power, current, and also your single line diagram represent component details. What component you are using, what's its rating. So first we are going to understand how we are representing the technical parameters of each component in our single line diagram. So first we are going to understand representation part, how we are representing the technical parameters of each component in single line diagram, and then in last we learn how we are preparing the single line diagram for any electrical system. Just see. So first we are going to understand bus bar representation. How we are representing the details of a bus bar. So this line basically called bus bar. Okay. After drawing this line, we are representing the details of this line, details of this bus. So what detail of this bus we are representing? First we are representing the details. First we are representing the voltage detail of this bus. First we are representing voltage detail of this bus. Second we are representing current rating of this bus. Third we are representing fault current rating of this bus. And fourth we are representing what type of conductor, what type of material we are using for this bus. So four parameters we are representing: voltage rating of bus, current rating of bus, fault current rating of bus, and what material and conductor we are using for this bus. These four details we are representing. Now first, how we are deciding the voltage rating of this bus? For example, this bus is connected with two numbers of incoming feeder, and your incoming feeder voltage rating is 132 kV. So your bus voltage rating is also 132 kV. Means bus voltage rating is equivalent to connected feeder voltage rating. Means whatever feeders are connected with this bus, whatever their voltage rating, that is the voltage rating of your bus. So bus voltage rating is equivalent to connected feeder voltage rating. Okay. So for example, this bus is connected with two numbers of incoming feeder, and each feeder voltage rating is 132 kV. So your bus voltage rating is also 132 kV. The next is the current rating. How we are representing the current rating of this bus? For example, this bus is connected with two numbers of feeder, and feeders are running at voltage level 132 kV, and power is flowing through this feeder is 100 megawatt each. Each feeder power is flowing 100 megawatt. So how much total power is coming on this bus? That is the 200 megawatt. From a feeder 1, power is coming 100 megawatt. From a feeder 2, power is coming 100 megawatt. So total power coming on this bus is 200 megawatt. Then next, what you are doing, based on feeder power rating, based on your bus power rating, that is the 200 megawatt, and bus voltage rating 132 kV, we are calculating current rating of this bus. So current rating, how we are calculating? So we are calculating current rating by this equation: power, that is the 200 megawatt, divided by voltage, that is the 132 kV, into root 3. Root 3 value is 1.32. So by this equation, we are calculating the full load current rating of this bus. Okay. So this current rating is coming, for example, in this representation 1250 ampere. After representing the current rating, next we are representing the fault current rating. So fault current rating is equal to your incoming feeder. If your incoming feeder fault current rating is 40K, so your bus fault current rating is also 40K. So bus fault current rating is equivalent to incoming feeders. The next one is type of conductor. What type of conductor we are using for a bus construction? What type of conductor? So these things we are decided based on calculation. These things we are decided based on calculation. what type of conductor you are using. So these things we are going to learn in coming classes, how we are deciding the conductor. But till now you represent here ACSR conductor. Till now you represent here ACSR conductor. Okay. Now, so these are the details we are representing for any bus. So wherever you are preparing the single line diagram, first you are drawing the bus and then you are representing the details of all these buses. After bus, next equipment is transformer. So this is the symbol of transformer, you know very well. This is the symbol of transformer, and left side we are representing the technical parameters or technical details of this transformer. So this is the symbol. First you are drawing the symbol of transformer, and then left side you are representing the technical parameters of transformer. So what details of transformer you are here representing? First you are representing the type of transformer, what type of transformer you are using in your system. Basically, if you see different types of transformer, you have a power transformer, you have a LT transformer, you have a auto transformer. So what type of transformer you are using in your system, first that you mention here. After defining the type of transformer, next you define voltage rating of your transformer. So voltage rating of transformer, always we are representing like first primary winding voltage rating, then secondary winding. Primary winding means though winding power enter in your transformer, that is called primary winding, and though power out from your transformer winding, that is called secondary winding. So here 33 by 130, that means the primary winding is 33 kV through power in your transformer, as secondary winding is 132 kV. That means ki your transformer is a step up type. Your transformer is a step up type. Okay. Next we are representing the MVA capacity of transformer. Means what rating of a transformer you are using in your system. You are using 10 MVA transformer, 5 MVA transformer, 100 MVA. What rating of a transformer you are using in your system, that rating of transformer here you are mentioning. After rating of transformer, next things you are mentioning cooling method of transformer. So cooling method of transformer means in transformer we are using different type of cooling method. Okay, in transformer we are using different type of cooling method. So we have a ONAN type of cooling method. Full name of ONAN means oil natural air natural cooling method. Oil natural air natural cooling method, ONAN. Second type of cooling method is ONAF. ONAF, oil natural air force cooling method. ONAF, oil natural air force cooling method. Third we have a OFAF, oil force air force cooling method. So this is a different cooling type of cooling method of transformer. Why we require cooling method in transformer? So you know very well when your transformer is running, so your transformer is heated, so we require to cool the transformer. So we are using different methodology to cool the transformer. So these are the methods of cooling. So when we talk about ONAN cooling method, so oil natural or air natural, ONAN, oil natural air natural, this cooling method we are using up to 10 MVA transformer. ONAF cooling method, this cooling method we are using in bigger size transformer, means up to 100 MVA transformer we are using. More than 10 MVA and up to 100 MVA, not 100, more you can say up to 150 MVA transformer we are using ONAF cooling method. Then third type of cooling method is called OFAF. So OFAF type cooling method we are using in bigger size of transformer, those transformer rating more than 200 MVA. So there we are using OFAF type of cooling method. After cooling method of transformer, next we are representing the percentage impedance of transformer. percentage impedance of transformer means this is the your calculated impedance value of transformer in per unit method. This is the calculated value in per unit method. So your transformer percentage impedance value depends on two parameters. First, it depends on transformer MVA capacity, what transformer you are using in system, and second depend on system fault current rating. So this value calculation I am going to guide in coming class. I am guiding you fault current calculation.
Sir.
That time I am going to guide you how we are calculating the Hamid, tell me.
Not audible, sir.
Now my voice is audible.
Just
Now, yes.
now.
Okay. So this is the percentage impedance. So just note down a standard percentage impedance value based on MVA capacity. A standard percentage impedance value. A standard percentage impedance value based on MVA capacity. You just prepare a one table. Serial number, transformer rating in MVA, transformer rating in MVA, and then third one is percentage impedance value. First serial number, second transformer rating in MVA, and third percentage impedance value. Okay. Now serial number 1, transformer serial number 1, transformer rating up to 5 MVA, not 5, up to 2.5 MVA. Transformer rating up to 2.5 MVA, percentage impedance value 4.25. So your transformer rating up to 2.5 MVA, percentage impedance value is 4.25. Then next your transformer rating 5 MVA. Next your transformer rating 5 MVA, percentage impedance value is 5%. Then next transformer rating up 6 MVA to 10 MVA, 6 MVA to 10 MVA, percentage impedance value 6.25, 6.25. Then your transformer rating 12 MVA to 25 MVA, 12 MVA to 25 MVA, percentage impedance value 7%. Then your transformer rating 30 MVA to 45 MVA, 30 MVA to 45 MVA, percentage impedance value 8%. Then your transformer rating 50 MVA to 150 MVA, 50 MVA to 150 MVA, percentage impedance value 10%. Then next your transformer rating 180 MVA to 250 MVA, percentage impedance value 12%. 180 MVA to 250 MVA, percentage impedance value 12%. Then your transformer rating 315 MVA, percentage impedance value 14%. Then your transformer rating 500 MVA, percentage impedance value 15/16%. So this is the standard percentage impedance value based on MVA capacity. Next one, after here if you see this transformer rating is 65/75, so here percentage impedance value is 10% at 75% MVA. Then next we are representing the vector group of your transformer. Vector group of your transformer means if you see this is a three-phase transformer, so how winding of transformers are connected. So normally we have a two type of connection, a star connection and second one is the delta connection. So this vector group represent how your transformer windings are connected. Your windings are connected in a star or your windings are connected in delta. Means sometime what happen, your primary winding is connected in a star, secondary winding is connected in delta. Sometime what happen, both winding are connected in a star, So how your windings are connected, that representations are vector group. So if you here see, your transformer vector group is Y capital, N capital, a small y, N a small 0. That means here first we are representing the HV winding connection in capital letter. So your HV winding is 132 kV. It's connected in a star connection with neutral. And then in a small letter we are representing the LV winding. So LV winding is 33 kV. It's also connected in a star with neutral, a small y, a small n, and 0. So vector group, how we are representing? First we are representing the HV winding in capital letter, then LV winding we are representing in a small letter. Like that we are representing the vector group of transformer. For example, your here HV winding is connected in delta and LV winding is connected in a star. So how you are represent? D capital means delta, Y a small, N a small, 1 1. So when your HV winding connected in delta and LV winding connected in a star, so how vector group you are representing? D capital, Y a small, N a small, 1 1. So there we are using 1 1. 1 1 why we are using? When you have a different connection, means when you have primary and winding, primary and secondary winding have a different connection. So in this case, what happens? There is a phase sequence difference between primary and secondary voltage. So that phase sequence difference we are representing by 1 1. 1 1 means 30-degree phase sequence difference between primary and secondary voltage. When both windings are connected in same, so their phase difference value is 0. So if you see here a star connection, so phase difference value is here considered 0. After vector group, next detail of transformer we are representing the tap changer detail. What type of tap changer and what rating of tap changer is connected with your system? So normally if you see here, so two type of tap changer we are using in our transformer. One is called OLTC, on load tap changer, and second we are using OCTC. OCTC means off circuit tap changer. So two type of tap changer we are using: OLTC, on load tap changer, OCTC, off circuit tap changer. So when we talk about OLTC, this is the on load, means tap changer basically we are using to control the voltage fluctuation of transformer. Sometimes what happens, suddenly voltage start fluctuation. So that voltage fluctuation we are controlling with the help of tap changer. So OLTC tap changer we are using in big size of transformer. Those transformer rating is more than 10 MVA, there we are using the OLTC. So in this type of tap changer, what happened? Your transformer are in running condition, load condition. If there is any voltage fluctuation, so automatically numbers of turn of transformer is changed. That is called OLTC type of tap changer. Okay. Now OCTC, off circuit tap changer, always we are using in a small size of distribution transformer. Means those transformer are distribution transformer and their rating is below 10 MVA. So on those transformer we are using OCTC, off circuit tap changer. So how, for example, in this there is any distribution transformer, you can say utility transformer, and suddenly voltage is low or fluctuate. So how voltage fluctuation we are controlling? First we are off the transformer and then by manually method numbers of turn of transformer we are changing. So that method is called OCTC method of tap changer of your transformer. So OCTC we are using below 10 MVA transformer and OLTC we are using above 10 MVA transformer. So this range OLTC and OCTC depend on wherever you are installing the transformer, there how much chance of voltage fluctuation. So for example, this transformer wherever installed, there is chance of voltage fluctuation plus 5 to minus 15%. That means the voltage increase by 5% or decrease by the 15%. So this is the range of a tap changer. So these are the details of a transformer we are representing in a single line diagram. First we are representing the type of transformer, then voltage rating, then MVA capacity, then cooling method, then percentage impedance, then vector group, and then tap changers. Understand, Hamid and Ganesh, what details of transformer we are representing in a single line diagram?
Yes,
Yes,
sir.
sir, but I have one question only. This 16 steps, what does it mean?
16 steps means if you see tap changers has a numbers of turn. Okay, transformer has a winding and those winding a numbers of turn. So you
Okay.
cannot change the in a one step. Means for example, suddenly your voltage down. Okay, so you cannot suddenly increase the numbers of turn of your transformer. So what happens? Your system has a huge voltage fluctuation. So we are changing the numbers of turn of your transformer means by some steps. Okay. So plus 5 to minus 15, that is the total range of your tap changer is 20%. Means 20% is voltage fluctuation in your system. So this 20% voltage fluctuation you cannot cover in a one time. So these things you cover in a steps. So one steps you are cover 1.25%. So that means ki 20% divided by 1.25%. That means ki how much, how many steps you require? Minus
Okay,
15 to
16.
plus 50, 16 steps.
Yeah.
Now, after transformer, next equipment is your breaker. After transformer, next equipment is breaker. So here we are going to discuss about breaker representation. See how we are representing the breaker details. Okay. So this is the your breaker symbol, and left side we are representing the details of a breaker. So what details of a breaker we are representing? First we are representing the voltage rating of breaker. Second we are representing current rating of breaker. Third we are representing type of breaker, and fourth we are representing current breaking capacity of breaker. So four detail we are representing: voltage rating of breaker, current rating of breaker, type of breaker, and breaking capacity of breaker. So how first we are deciding the voltage rating of breaker? For example, this breaker you are installing in any feeder, and that feeder voltage rating is 132 kV. So what is the voltage class of your breaker? 132 kV. So voltage rating of your breaker is equivalent to feeder voltage. Whatever your feeder voltage, that is the voltage rating of your breaker. So breaker voltage rating is equivalent to feeder voltage rating. Next one is the current rating. How current rating you are deciding? So for this we are calculating the we are doing the some calculation. So current rating of your breaker depend on two parameters. First, how much power is flowing through your feeder and at what voltage level. For example, somewhere you are installing this breaker, and that voltage feeder is working at voltage level 132 kV, and power is flowing through feeder is, for example, 100 megawatt. So how you are going to decide current rating of breaker? So for this, first you are calculating the full load current. So full load current, how you are calculating? Power divided by √3 into voltage. By that equation you are calculating the full load current. So your power is 100 megawatt. So your feeder power rating is 100 megawatt. So first you calculate current rating. So means your feeder power rating is 100 megawatt. So first you current full load current rating. So 100 megawatt, first you convert in kilowatt. So multiply by 1000 divided by 1.732 divided by feeder voltage rating 132. So what is the full load current rating is 337.4 ampere. So your first we are calculating the full load current, and this value is coming how much? This value is coming 337.4 ampere. After calculating the full load current, next we are calculating the breaker rating. So breaker rating, how you are calculating? Full load current multiplied by 1.25. So your calculated full load current power divided by voltage into 437.39 ampere. Now you multiply by 1.25. Breaker current rating is how much? 546 ampere. So this is the required rating of a breaker, 536 ampere. Now 536 ampere breaker is not available in market. Whoever manufacturing the breaker, they are making the breakers for some standard current rating. Okay. So if you see this table, so first row is represent voltage class of your breaker and then current rating of a breaker. So if you see your feeder voltage rating is 132 kV, this is the 132 kV, and your calculated breaker current rating is coming 546 ampere. Means for this feeder, required breaker rating is 546 ampere, but 546 ampere breaker is not available. What a standard rating of breaker is available? Minimum size 630 ampere, then 800 ampere, 1250, 1600, 2000 ampere, 12 and 2500 ampere, 3150 and 400 ampere, 4000 ampere. So your calculated breaker current rating is coming 546, but 546 is not available. So what you are doing? You are selecting the breaker current rating is 630 ampere. Similar way, for example, your calculated breaker current rating is coming 1100 ampere. So again, if you see this table, so 1100 ampere breaker is not available. So what higher size breaker current rating is available? 1250 ampere. So you are selecting 1250 ampere breaker current rating. So you understand how breaker current rating you are decided, Hamid and Ganesh?
Yes, yes, sir.
After current rating of breaker, next we are deciding the type of breaker. So normally we have a three type of breaker. First we have a ACB, air circuit breaker. Second we have a VCB, vacuum circuit breaker. And third we have a SF6 circuit breaker. ACB, air circuit breaker, we are using in low voltage system. Those feeder voltage rating is up to 3.3 kV. So up to 3.3 kV feeder, we are using the air circuit breaker. In medium voltage system, medium means 6.6 kV to 33 kV system, 6.6 kV, 11 kV, 22 kV, 33 kV, 15 kV. So 6.6 kV to 33 kV system, medium voltage system, we are using VCB, vacuum circuit breaker, as well as SF6 circuit breaker. So now here question is coming in medium voltage system 6.6 kV to 33 kV, so where we are using the VCB and where we are using the SF6 circuit breaker. So VCB we are using in those feeder fault current rating is up to 31.5 kV. Means those feeder are running up to 33 kV voltage level, means those feeder voltage rating between 6.6 kV to 33 kV and fault current rating is up to 31.5 kV. So there we are using the VCB, vacuum circuit breaker. And those medium voltage feeder 3.3 kV to 33 kV feeder, fault current rating is more than 31.5 kV. There we are using the SF6 circuit breaker. Understand? So in case of medium voltage system, we have a both option VCB and SF6, but VCB we are using up to feeder fault current rating 31.5 kV. If your medium voltage system fault current rating is more than 31.5 kV, we are using SF6. And in EHV system, means 66 kV to 765 kV system, we are using only one type of breaker, SF6 circuit breaker. Understand, Ganesh, where we are using ACB, where we are using VCB, and where we are using SF6 circuit breaker? Is there any doubt?
Yes, sir. But can you explain why up to?
I'm
33?
explaining.
Okay.
Now this is the classification. You understand like where we are using VCB, where we are using SF6, right?
Yes, yes.
Now we have a three type of breaker. First one is you have a air circuit breaker. Second you have a SF6 circuit breaker, VCB, vacuum circuit. Third one is SF6. How these breaker are classified? So these breaker are classified based on arc quenching medium. Arc quenching medium means if you see any feeders, so breaker has a contacts. So when your breakers are opening, so surrounding the breaker contacts huge arcing, huge ionization. Understand? So those ionization, those arkings we are quenching by different medium. So when we are using the air blast, high pressurized air to quench the arc surrounding the breaker contacts. So those type of breaker is called air circuit breaker, ACB type breaker. And those breaker where are surrounding the breaker contacts, arc we are quenching with help of vacuum. That breaker is called vacuum circuit breaker. In those circuit breaker, arc quenching we are doing with help of SF6 circuit gas. So that type of circuit breaker is called SF6 circuit breaker. Understand? Now, in low voltage system, up to 33 kV system, when your breaker opening and closing, that time limited amount of arc surround contacts are can quench with
Not
help
clear,
of
sir.
air pressure. Okay. Now my voice is audible.
No, now
Hello?
yes, but before no.
So I am saying in low voltage system we are using air circuit breaker. Okay. But in low voltage system, when your breaker is open and breaker you're closed, so surrounding the breaker contacts you have a less. Okay. And those arc you can quench with help of air pressure. Okay. But once you go in medium voltage system, so there when breaker open and close there is a huge arc because of high voltage system. So those arc you cannot quench with help of air system. You require vacuum or you require SF6. Understand why
Yes,
we are
yes, sir.
using air circuit breaker in low voltage? Is the classification. And third, we are representing the fault current rating of a breaker. Fault current rating of breaker means कि, for example, this feeder you are using in 132 kV and 132 kV standard fault current rating is 40 K. Means those feeder fault current rating is 40 K. So your breaker breaking capacity is 40 K for 3 seconds. Understand? Understand?
Yes,
How
sir.
you are decided now. So this is the breaker representation part. After breaker, next component is your isolator. Okay. So your breaker is your on-load switching device. When your feeder are in running condition, that time you can on or you can off the breaker. But your isolator is off-load switching device. Okay. Isolator normally on or off in case of off-load condition. Okay. Now, so this is the symbol of isolator, and left side we are representing the isolator details. So what isolator details we are representing? First we are representing the voltage rating of isolator. Second, current rating of isolator. Third, type of isolator. And fourth, breaking capacity of isolator. So if you see, isolator representation is similar to your breaker representation. Understand? Isolator representation is similar to your breaker representation. First you are representing the voltage rating, second current, and then type of isolator, then breaking capacity. Now you have a three type of isolator. First one is called motorized type of isolator, and second one is manual type of isolator. So you have two type of isolator. First one is motorized type of isolator, second one is the manual type of isolator. So in manual type of isolator, these isolator blades you are opening by manual method, by with help of handle. In motorized type isolator, you are opening these blades from a control loom with help of one signal, with help of motor. So this is called motorized type of isolator. Now, manual type of isolator we are using up to 11 kV system, and above 11 kV system we are using motorized type of isolator. So up to 11 kV system, what type of isolator you are using? Manual type of isolator, and above 11 kV system you are using motorized type of isolator. Now how isolator representation we are doing? So if you see this isolator, for example, this isolator we are using in any feeder, and that feeder voltage rating is 132 kV. So your isolator voltage rating is 132 kV. Current rating representation is similar to breaker. Whatever current rating of breaker is available in market, same current rating of isolator is available. So therefore, isolator current rating is equivalent to feeder breaker rating. For example, this isolator you are using any feeder, and in same feeder you are using the breaker. So whatever current rating of breaker you are using, same rating of isolator you are using. Basically, isolator current selection method is same as breaker current rating selection method. Okay. Then next one is the type of isolator. So I have already explained to you manual type isolator and motorized type. So above 11 kV system we are using motorized type of isolator. Once you remove this M from this symbol, so this isolator is called manual. This M basically represent motorized type of isolator. And then last we are representing the fault current rating of isolator. If you see this isolator and this isolator, so there is a difference. This difference is this earth switch. In this isolator there is a no earth switch. In this isolator there is a earth switch. Okay. So this type of isolator is called with earth switch. This type of isolator is called without earth switch. Now here question is coming to what's the role of this earth switch. So this earth switch we are using for a safety purpose. Okay. So somewhere we are using this earth switch with isolator, somewhere we are not using this earth switch with isolator. So how earth switch position we are decided, these things I am going to guide you once we learn the complete single line diagram part. That time I am going to guide you how earth switch position and earth switch quantity we are decided. So Hamid and Ganesh, understand isolator representation or is any doubt?
No.
No doubt, sir.
Okay. So today we have gone through up to isolator part. Okay. In next class we are going to discuss about next component. We are going to discuss about surge arrestor, CTPT, relays, other equipments. Okay. And then
Okay.
in tomorrow class we are going to understand how finally we are preparing the single line diagram. Understand Ahmad and Ganesh?
Yes,
Yes,
sir.
sir.
So tomorrow be available at same time. Okay.